So welcome back. We have the pleasure to have Vitaly Feldman here with us. He's at Apple, and he works on machine learning and privacy. Before that, he did his PhD at Harvard University under Leslie Valiant, and then he also has a lot of experience at Google. So he was also Google Research and IBM Research before joining Apple. His work has received a lot of Best Paper awards and other awards. For example, in his work received an award in 2021, the Caspar Bowell Award for Outstanding Research in Privacy Enhancing Technologies. And we're so happy to have him here, so please go ahead.
Thank you, Antigone. Thank you to all the organizers for inviting me, and all of you are coming. I just learned that I'm lucky that I'm here. Many people could not, but I guess you are too. I'm going to talk about low communication algorithm for private federated learning that have optimal accuracy guarantees, in the sense that they'll have the optimal trade-off between the privacy and utility. I would like to encourage you all to ask questions. Some of the parts of the talk will be a little bit technical, so I'd rather have you stop, just raise a hand, and I might need to repeat your question. So let's go. So let's start with the basic setup, and we'll be looking at federated data analysis, in which we have clients or client devices. Think of those phones as or wearables or browsers, where each of those devices belongs to a single user. And each user is holding a data point. For simplicity, we'll assume just a single one, and there will be n of those users, and we'll denote them x1 through xn. And we'll have a server that wants to communicate with those devices so as to perform some kind of data analysis. And it should be clear at this point that we need a lot of data analysis are necessary to be able to provide users with various useful functionalities. For example, we may want to perform some kind of performance analytics to be able to improve applications. We may want to provide users with some recommendations. We may want to do speech recognition for digital assistants, or solve problems such as word prediction, which themselves usually decompose into smaller tasks, such as discovering new type words, or training and tuning language models. There's a huge number of possible analysis tasks or applications one might want to do. But luckily for us, many of those can be reduced to two relatively simple kind of basic problems. And those are the following. The first one is frequency estimation, or building a histogram. And in this problem, we think of each users as holding an element in the domain, which from 1 to k. And the goal is just to estimate the frequency of each of those k different elements. And the frequency is just the number of times it occurs among all the users. And the error in this setting is typically, there are many ways to define the error, but a common notion of error, the one will be just for concreteness focusing in this work, is the sum of squared errors over all the k elements of our estimate of the frequency. So that's one important building block, and one which is used, for example, in more complicated algorithms, such as finding heavy hitters. And the other building block for many learning algorithms is L2 high-dimensional mean estimation. And in this problem, each user has a vector, a d-dimensional vector. Typically, we'll assume that it has some bounded norm, for example, norm at most 1. And our goal is to just estimate the mean vector among of the vectors held by the users. And here, the estimate, as before, we'll be looking at the minimizing the squared error, expected squared error of our estimate. So this problem, I imagine most of you recognize, is the sort of the basis of gradient descent-based algorithms, which are, of course, the bread and butter of machine learning today. So these are simple problems, and one rejected, why can't we just solve those? And the answer is simple, given this conference, is that a lot of the data held by devices is sensitive, and users may not be willing to share it, or it might be not possible to collect that data if we don't provide users with some sort of privacy guarantees. And of course, preserving privacy is a complicated, a system-level problem, which has many ingredients. But one ingredient which became kind of important in recent years, and one which has been first proposed in academia and now adopted in industry, is the use of this local differentially private randomizers, which basically says that we'll take the data, and before the data leaves the device, it is randomized in some way so as to conceal the sort of signal and limit the amount of information that is will be leaked about the user data. And the idea is not new. In fact, it has been the idea already been used in for conducting sensitive user studies or surveys in social scientists by Wagner in '65. It has been discovered by database community in 2003, and then sort of kind of cast into the language of differential privacy in this paper of Kasiviswanathan et al. In 2008. And more formally, I imagine many of you know the definition. It basically says the following: for any pair of two different inputs that a user might hold, the output distribution produced by the randomizer that we run on this data, these output distributions are similar. And what does it mean to be similar? The ratio of densities is always at most e to the epsilon for every possible output element. So effectively, one way to think about it is whatever you know about whatever prior information you have about the user, your posterior information will not be changed by more than this factor of e to the epsilon. So the epsilon here, as you can imagine, is the specific amount which measures the data privacy, the amount of privacy that is being provided, or the amount of information that is could be leaked. And it's a natural question as to what this epsilon should be. And for the purposes of this talk, we'll focus on epsilon being a small constant, which is larger than 1, but not too large, for example, 5 or 10. And the reason for this choice is that even though we would ideally like epsilon to be very small, having this kind of privacy guarantee does come at a cost in utility. There is an effect on privacy. So the more on accuracy, the more privacy you provide, the less accuracy you get. And in practice, it has been discovered that to get reasonable utility, you need to take values of epsilon larger than 1. And this might seem like not such a great privacy guarantee in itself, but one way to think about it is as only part of the picture. It's only one of the privacy protection one gets. For example, if the system in addition includes a component that shuffles these random reports, then privacy before the data reaches the server, then the privacy guarantees that the one will get for this shuffled reports will be amplified. This is so-called privacy amplification by shuffling, and this amplification will ensure that even starting from this relatively not so small epsilon, one can get very strong privacy guarantees, at least if one trusts the shuffler and so on. So, but at the very least, this is it's one type of guarantee that one gets, that whatever leaves the user device will not have, you will not leak more information than what's guaranteed by this epsilon. And to give you a bit of an idea and a bit of an example of how one can randomize data, specifically in the context of the two problems that I've mentioned, let me give you two examples of randomizers. The first one is for frequency estimation. It was proposed in the context of this rapport system by Erlingsson et al., which was deployed by Google in 2014. And it's the following very simple randomizer. It starts with you're given an index, which is an element from 1 to k. First, as a first step, it's converted to one hot encoding, which is just an indicator vector of that index, which is 0 everywhere, except it's 1 in the position in the index, which is the value of the element. And then the 1 in that encoding is replaced with the random coin flip with probability 1/2. And every 0 is replaced with a random coin flip with the bias 1 over e to the epsilon plus 1. And this replacement happens randomly and independently. It's a simple algorithm. It's very easy to see that it satisfies this epsilon local differential privacy. That's one algorithm. And here's another simple example for the problem of mean estimation, one way to randomize, or maybe one of the most well-known ones, is to take your input. First, you usually need to clip or project it back to a certain norm, for example, norm 1, to ensure that the input is not unbounded. And after that, one can just add noise, such as Gaussian noise would be the most commonly used. And for appropriately chosen parameter sigma, it will give privacy guarantees, although it, without modification, it only gives approximate differential privacy, but could be modified to give this pure epsilon differential privacy in this case. So these are two simple examples. And now I can tell you a little bit more about the problem that we're trying to address in this work. And basically, the problem is that the following state of the art, or at least prior to our work, or to my work with several colleagues, the state of the art in this area was the following. One, for both of these basic problems, one would have to do one of these two compromises. The first would be to use an algorithm which has communication cost, which scales linearly with the dimension in the mean estimation problem, or domain size in the frequency estimation problem. Or if you wanted to go low communication, wanted to use a low communication algorithm, one would have a suboptimal privacy accuracy trade-off. And here, suboptimality does not mean asymptotic. It's actually suboptimal by a constant factor, typically larger than 2, which might not seem like much, but in practice, it's a significant suboptimality, which affects many downstream tasks. So definitely something we want to eliminate. So, and maybe I should note that this suboptimality is particularly problematic for frequency estimation, because in the frequency estimation, the communication scale linearly with the entire domain size. And the domain size, we do want to make this domain size to be large. And moreover, the signal, sort of the index itself, only contains log k bits of information. But in order to randomize it with optimal privacy utility trade-off, we had to use algorithms which sent k bits, or something which scales linearly with k bits. So now that's the problem, and let me overview the kind of results that we have for this problem. So the first one is in a joint work with Kunal Talwar, and the way we describe it is a general lossless compression of efficient local differentially private randomizers. But what it effectively does, it takes an arbitrary computationally efficient local randomizer and replaces and gives a version of it which is has essentially the same privacy guarantees, essentially the same utility guarantees, but on top of it has very low communication. So it basically replaces your randomizer with a low communication one, and a high level says that this communication is not at odds with optimal trade-off. Whatever trade-off you can achieve with high communication, you can also achieve it with low communication. So for this general result, I'll describe the general result. I also give some specific application of this result, sort of simpler forms of it, which apply to specifically the problems of frequency and mean estimation that I've mentioned. So one disadvantage of this kind of direct application is that the algorithm that we get, it has low communication, but it has not such great server computing time. And we have an algorithm which uses somewhat related ideas. And it's, first of all, joint work with Jelani Nelson, Hu Nguyen, and also Kunal Talwar, where we show that one can also achieve a much better server compute time for the problem of frequency estimation. The situation for the mean estimation was even less clear. There, it wasn't even known what is the optimal or trade-off between privacy utility trade-off for every epsilon. And in a recent work with Hilal Assi and Kunal Talwar, we demonstrate that one existing algorithm that has been known for an appropriate choice of parameter is the optimal algorithm, and we show that this is basically, we discovered that the optimal trade-off. And we also give a new algorithm which is somewhat simpler than the one that was known before. but it is still optimal. And finally, as I mentioned, this local privacy guarantees are only maybe a piece of the whole system. I also show that the ideas that we are using for this maybe simpler setup of optimizing just a local randomizer can be used when optimizing local randomizer in a sort of a more complicated setup, which involves secret sharing, where we want to make sure that the server doesn't observe the entire all the individual reports. They go through some kind of secret shared aggregation, and we want to make sure that the low communication protocols that we design support this secret sharing. So that's a high-level overview. I'll start one by one, telling you a little bit more about those results. Let me know if you have any questions so far. Great. Either people are asleep after lunch, or everything is very clear.
Question.
Yes. Yes, you can just shout it out. Well, that's sort of the well, maybe the one root issue is that it's harder to design algorithms that have low communication and in addition are optimal. It's just I think at least in one case we have discovered an algorithm which could have been discovered before our general conversion or this general insight, but for whatever reason it hasn't been. Where even though people certainly have tried, and I'll discuss in a second prior work in more detail and our results in more detail. I don't think there is people have realized that local differential privacy should imply that because effectively very little information is being leaked. So it shouldn't take too much communication to communicate that. But and people have had ways to exploit this, but they either lost in the conversion, they doubled or sometimes quadrupled the epsilon, which kind of ruins things. And there are other issues. I mean, it's maybe a longer story why it hasn't been. It's a good question. I think there is nothing fundamental. It's just somehow that was the state of the area before we started looking at it. Anyway, so the first result is the general lossless compression. And let me start by actually describing you pretty much in full what this result states. So we'll start, what we say is for every epsilon differentially private, computationally efficient local randomizer, which maps from X to some output Y, there exists a different epsilon differential local randomizer, which R prime, which will be mapping from X to some Z. And should think of this Z as being seeds to some pseudorandom generator. We'll see more about it in a second. And we'll also have a certain decode procedure which maps from Z back to Y, the original output domain, with the following property. So first of all, note that this R prime is still an epsilon differentially local randomizer, so privacy is preserved. And the property and the other utility is preserved in the following sense, is that the decoding of the output of this R prime of X is computationally indistinguishable from the original randomizer. So utility will be preserved, provided that you're doing computationally efficient post-processing on that output. So maybe first I should note that computational efficiency here is not just computing the actually sampling from the randomizer. It also involves being able to efficiently estimate the densities given by this randomizer, which is true for the kind of randomizers we know. But in general, it's a somewhat different requirement. Density estimation and sampling are different computational procedures. So that's the result. Let me tell you. Okay, so maybe okay. What I didn't say is, I said that we have compressed from this Y to this space of seeds, and the question is how long are those seeds, how much communication we're actually saving. And so in theory, in this general result, yes. Yeah, X is the space of the user data. Y is the space into which you randomize things and then send that report. So this is typically something large. For example, again, imagine this binary, this one hot encoding, which was randomized, a long space. Z is the kind of this compressed version or of Y. And we need to decode from this compressed version back to the original, the same domain as Y was originally. So, and now I'm discussing the size of this Z. In theory, basically, the size depends on the strength of the cryptographic assumptions. But if you assume that you have PRGs that are that can fool exponentially large circuits, then you can always send a seed whose length is logarithmic in the problem size. So it's short. In practice, you can always send your system PRG of 256 bits, and that will be enough. And maybe more importantly is that this is a very general result, but for specific randomizers, we can use simpler unconditional PRGs, which are tailored to the specific randomizer. We don't have to use a general PRG, general cryptographic PRG for specific problems. And that's one of the things we'll do for our applications. So that's the statement of the result. Let me give you a little bit of intuition. Overall, this is not a technical talk, but I want to give you a bit of a sense of why PRGs, why sort of maybe the part which should look somewhat mysterious to you is that differential privacy is information theoretic guarantee. It's completely non-computational. And we are using some kind of cryptographic assumption to still preserve this information theoretic guarantee. We are not, there are versions of differential privacy which are more computational, but we're still using our computational assumption to preserve information theoretic guarantees. That, at least some of you should be somewhat puzzling. So let me give you a bit of intuition about this result. So here is, and I'll do this by completely describing this algorithm that we're using for low communication version of the same, this sort of losslessly compressed version of the original randomizer. So, okay, we're starting again with this randomizer R, mapping from X to Y, and we assume that it's efficient, epsilon differentially private. So we will need to fix some sort of reference distribution. And for this, we will pick one of the elements in the domain, arbitrary one, say 0, and we'll denote it by X0. And the reference distribution that we need to fix will be the output distribution of our randomizer on that fixed element. So there'll just some fixed distribution will be denoted by R of X0. And what is and this is the distribution from which we can sample from this fixed distribution, because we can just apply R to this element X0. So because we can sample this from this distribution, we can think of some algorithm which we will just denote as this algorithm as R0, which samples from the distribution. What is a sampling algorithm? It's an algorithm which takes a random binary string, random uniform binary string, and outputs an element in the domain of the distribution, right? So it's just a deterministic algorithm which takes a Boolean string of length t, and if you feed it and outputs an element, and if you feed it random uniform bits, it will output an element from the output distribution R of X0 from this reference distribution. Okay. Now we have a way to convert bits to output elements for the reference distribution. We'll also need a PRG, which is something that, so this reference distribution, sampling reference distribution may require lots of bits. We'll also use some kind of PRGG, which will take a small number of bits and create a L, and will create a large number of random bits, well, pseudo-random bits, T. So these are the ingredients we'll need for the algorithm. I can now describe the algorithm, and it looks the following. Informally, it's basically rejection sampling. So we have this reference distribution, And differential privacy guarantees that this reference distribution is not too far from the any distribution that we may want to output when we're given an input element, some input element. So because it's close, we can do rejection sampling. We can sample from one distribution and reject if if the ratio of density is whatever, by flipping some random variable, which is equal to the roughly the ratio of densities, we can do rejection sampling by using this reference distribution. And the only tweak to that we'll do to this algorithm is that instead of using this simple rejection sampling, will to sample from the reference distribution, we won't be using the true random bits. We'll be using the pseudo-random bits to sample from the reference distribution. So here is the description. We have some parameterized by the pseudo-random generator G and failure parameter gamma. We'll have some input element X, and this is the failure parameter. We'll need to, in order to ensure that the failure probability is small, we'll need to repeat this rejection sampling many times, specifically that number of times. I can point for you. Here's the number of times. And here we just repeat it. What we'll do, we'll sample a random seed, a short seed. We'll turn it into a long random sequence, apply our reference distribution element creator, generator, and then we'll just do rejection sampling, where rejection sampling is just rejects if the ratio. No, it doesn't reject. Sorry, it flips with this bias, which is just the ratio of the density of the desired density to the density that we of the reference distribution. We'll multiply it by e to the epsilon, which gives us, we know that this value is at most 1. Everything is easy to see that it's legal, and this is and this works, except we now use these pseudo-random bits instead of through randomness. The and this is that's basically the algorithm that we get. And maybe the only thing that okay, so the other part is the decoding, and the decoding is simple. When given a seed, you can always convert. We have a way to convert a seed back to an element in the domain by applying first, expanding the seed into a large amount of randomness, and then applying our reference distribution generator to create an element in the domain. Now, the only sort of issue with this algorithm is that it does run the sampling in expectation e to the epsilon times. So we do lose something in computational efficiency here, but other than that, it's not even that much more complicated than the original randomizer. So let me just very briefly tell you why this works, and what sort of why do we get the guarantees that I have mentioned. And I won't go into too many details, but let me just mention that what we basically do is we analyze the conditions under which the privacy guarantees would be preserved. Yes. Yes, everything is discrete kind of implicitly here, because we assume that you can generate the output element using a finite number of random bits. And of course, you cannot generate an infinite precision with a random. Yes, we live in implicitly live in a discrete world. Yeah. So to formally analyze, we'll need to look at this, again, standard notion of fooling. We say that a certain PRG fools a family of tests, this script D, if for every and the test is basically just a Boolean function which takes as an input a random string and tries to tell whether this is a true randomness or fake randomness. So it outputs just a 0, 1, and a PRG fools the family of these tests if for any test the difference in the probability that the test accepts on true randomness versus it accepting it on the randomness generated by the PRG is at most beta. And now what we show is that for a specific family of distinguishers, which are just basically some sort of density ratio estimations. And the important part here is that these are, if you can estimate that efficiently, you can compute those efficiently. If you have a PRG for this particular family of distinguishers, then this algorithm that we have defined, its privacy guarantees are preserved up to this 2 times e to the epsilon beta, but this beta can typically be made to be exponentially small. So it effectively means that our privacy guarantees will be preserved. And the other part is that we, of course, we also need to preserve utility, but that's here it will be just usual computational assumptions because we're kind of effectively just replacing some random bits with pseudo-random, and here this is just a standard analysis. Anyway, that's just to give you a little bit of intuition about the result. Feel free to ask any questions if not, well, you don't need to. You won't need this result for the rest of the talk. So now let me tell you a little bit about the applications. And before going applications, let me just roughly describe what was the state of the art before this work for frequency estimation. So first of all, the algorithm that I mentioned, rapport, discovered back in 2014, we know that its error is actually was later discovered that is utility price trade-off is essentially optimal. And here we even know what this optimal error is. It has been kind of computed and proved in more recent work by Ye and Barg. And that's the value of this error, just a function of whatever n and epsilon and k. The problem with this algorithm is that it has communication k. And also an additional problem is that server compute is high because you need to basically add n times k, which could be very large. And there is a closely related algorithm which is referred to as subset selection, which is basically instead of independent bits, they are like a set of fixed size, random set of fixed sizes chosen. And that's that algorithm is actually truly optimal, and its communication is a little better, but not by much. Still has high server compute. For a number of algorithms which are kind of were developed in for the problems heavy hitters, a related problem can be shown to achieve sort of order optimal error, although only when epsilon is at most 1, while having both low communication and low server compute. So and those have been known for a while. As I said, the problem is that here order optimal, often order optimal by significant constant. More recently, there have been 2 algorithms, Hadamard, basically both based on Hadamard transform, which achieve order optimal error for all epsilons, have low communication and low server compute. But again, and order optimal here is already quite reasonable. It's just within roughly a factor of 2, but still not great. And maybe I should mention there is also an algorithm which is, if you allow public randomness, there was an algorithm which is referred to as local hashing, which is optimal at least for some values of epsilon, not all. And again, requires public randomness and has high server compute. But that's roughly the state of the art. So let me show what we can do it using our ideas. So for this, let's very quickly recall this rapport algorithm, which converts to this long vector and then randomizes all bits independently, creating a very long string of bits. But one relatively simple observation is that in order to preserve the utility and privacy of this algorithm, all we need is to make sure that these bits in this long string are pairwise independent. We don't need them to be entirely independent. We'll have both the utility and privacy if they're just pairwise independent. And pairwise independent strings, families of pairwise independent strings don't need to be long. We can communicate. There are shorter construction, in fact, standard in cryptography ways to do this. So, I mean, all we need is basically just a pairwise independent family of random strings with the right biases we need, because these are Bernoulli with some specific biases. And this can be done via standard construction, which is the most standard one is your subspaces of a vector space or finite field. Again, if you've seen it, you know it, but if not, it's simple modular arithmetic. The properties of these algorithms are as following. It communicates roughly of order of epsilon plus log k bits, a very short communication. We can show that it achieves the optimal privacy utility trade-off. It basically follows from general analysis, or can be proved directly. And it has the only thing which is not so great is the running time is sometimes better than the naive rapport algorithm, but sometimes not. It's basically only better when k squared is k is less than n. When k is less than n. So this is the running time. So it doesn't always improve on the running time of the original rapport. And this running time is the problem issue. Is what we have addressed in a follow-up work with Jelani Nelson, Huyen Nguyen, and Kunal Talvar. And let me very briefly describe this. What we do in this work is it's a kind of a similar idea, in the sense that we do need to create a set system with certain properties, specifically pairwise independence. And to do this, instead of using the standard vector space construction, we use so-called projective spaces. And a projective space of a vector space over a finite field is just space in which elements that are so that each element is a scalar multiple of the other are basically equivalent. So it's basically the set of equivalence classes where equivalence is defined by multiplying by a scalar. And the T minus 2-dimensional projective spaces form a pairwise independent subsystem with the nice properties. On top of this kind of construction, we use a better server-side decoding algorithm, which is based on dynamic programming. And together, this construction gives us an algorithm which still has low communication of epsilon plus log k bits, even better than our pi rapport. It still has optimal privacy utility trade-off. And now the server runtime is on the order of n plus k times e to the epsilon log k. Basically, it's much better. It doesn't have this k squared or n times k term. And importantly, the algorithm is not just nice theoretically, it's actually works in practice. And let me just briefly mention a little bit about the results of simulations. So for example, for epsilon equal to 5 and k being the domain of 3000, it is 50 times faster than our pi rapport, and only 5 times slower than the fastest algorithm so far, which kind of had reasonably good guarantees, although again, not optimal, but reasonably good guarantee. It's relatively easy to implement, and the code is now publicly available. Here are sub-measurements of the error. And this is a graph of the error as a function of epsilon for different epsilons for a specific frequency estimation problem, some zip distribution, some domain size. This is the domain size. This is the number of users. The blue line and the light blue lines are basically this. The dark blue line is subset selection, is the optimal algorithm which has high communication. The light blue line is our algorithm, which has exactly the same error, but now has low communication. And the lines above are two previous low communication algorithms based on Hadamard response. And they have low compute, but the error is higher, often by a factor of 2 or more. So that's all that I want to say about this problem. Let me now tell you a little bit about mean estimation. And this is a problem for which we actually know a little bit less than for frequency estimation in this context, but still, we're now know more than what we used to know. So first of all, I should note that this addition of maybe one standard algorithm that has been known for a long time is addition of Laplacian or Gaussian noise. And we know that this algorithm achieves order optimal error but its communication scales with the dimension d, and also the compute is high on the server because d times n. We have sort of the first algorithm which maybe could show was so this Laplace and Gaussian noise have been proven they don't achieve the pure epsilon, they approximate differential privacy. So there are some additional log factor in that optimality result. To avoid the first algorithm which avoids this log factor is this private half spaces by Ducci and others, which shows optimality, although only for epsilon smaller than 1, still with high communication and high communication. This has been improved to arbitrary epsilon to this algorithm referred to as priv unit, still high communication. The algorithms which do achieve low communication have been proposed based on so-called Cushion representation, first for epsilon smaller than 1 in my work with Guzman and Vempala, and more recently by Chen and others for arbitrary epsilon. And these are the first algorithms which achieve low communication, just epsilon times log 2d, and have order optimal error. And at least it wasn't known for any of the algorithm whether any of those is actually optimal. Although in practice, it has been known that this priv unit achieves empirically the best error. And this is we know the order optimal error for this problem behaves like this, at least asymptotically. So here are some, this as I said, best contact achieved by priv unit. Let me now describe some new results for this problem. And for this purpose, let me first tell you how this priv unit algorithm by Böhmig and others works. And it's an algorithm which is which again tries to send a vector of norm at most 1. Let's imagine norm being 1, and it's parameterized by 3 parameters. This r, which is a radius, gamma is some kind of offset, a little margin, and some probability p. And what it does, first of all, it samples from its support is a ball, a d-dimensional ball of radius r. It samples with probability p. It samples from this spherical cap, which is defined by moving by this margin gamma away from the sort of the in the direction, spherical cap in the direction of the input vector u. It samples from the spherical cap, so it's kind of biased towards the correct answer. And probability 1 minus p, it samples uniformly from the complement of that spherical cap. So this is algorithm which has 3 parameters, but only because we typically want this to be unbiased. So epsilon differential privacy and biasedness create 2 constraints. So there's effectively only 1 free parameter in this algorithm. And what we show is that for an appropriate choice of parameters, so this algorithm was proposed with a specific choice of parameters, but we show that there is always a choice of parameters for which this randomizer is optimal. And this is joint work with Hilal C and Kunal Talvar. We show that for every epsilon and d, there exists a choice of parameters such that this algorithm has the lowest variance among all unbiased local randomizers. So that's all that I wanted to say about this result. So now that we know what the optimal algorithm is, we can compress it using this generic technique. We don't have anything much better, although there is a version of algorithm which can trade off the generic scheme with trade off some of the accuracy for computational efficiency. We don't want to pay this e to the epsilon blow up. But these are let me just describe the results that this our optimized algorithm achieves empirically. And here the comparison. So this the only low communication algorithms prior to ours is SQKR by Chen and others. It achieves this is the error. Here's the error is on logarithmic scale. So this is gap of a factor more than 2. The priv unit, the original one, and private half spaces are just this red. The red one is because it doesn't work well for large epsilon. The original priv unit is this black line, and our optimized version is this green one. So you can just see that it's a significant improvement while having low communication. And it's again, it's I should have mentioned that this is a plot of expected squared error versus epsilon. So we want to see how it behaves for this epsilon in this small constant range. Okay, so that's all that I want to say about the mean estimation. And as I promised, I want to briefly tell you a bit about how these ideas can be taken, applied in this sort of more complex systems where we have additional privacy guarantees beyond just the local privacy. And specifically, we'll be looking at the setting where we don't want the server to observe the individual reports from the users. We want the server to only observe the aggregate or sum of the user reports. And moreover, we don't want to trust this aggregation to a single server. We want to do it via secret sharing. You've heard quite a bit already today about secret sharing, so I don't need to tell you about its advantages. There is no single source of trust, and the hope is that in each of those aggregation servers will not gain any information at all about user data, not even epsilon differentially private. So how will it work? We'll have each randomizer, instead of creating a single output, it will create actually a pair of output. For simplicity, we'll be secret sharing to just 2 servers, but it extends to more servers. Again, for simplicity, we'll think of this as randomizer creating 2 shares, and shares. The first shares will be aggregated by 1 server, and the second shares will be aggregated by the other server. And we want to then send these aggregates to the analyst in a way that kind of amplifies privacy. And we know that aggregation will amplify privacy, even just shuffling amplifies privacy, but aggregation has even better privacy amplification guarantees. So this looks like a relatively complicated setup, but we can show that we can reduce the problem of designing local randomizers for this setting to the following two randomizers with the following properties, and we'll call it this basically secret shared local randomizer. And it's a randomizer with the following property. It takes an input element in X, but it produces a pair of values, basically 2 secret shares. And of course, with the following property is that we have 2 decoding procedure, decode 1 and decode 2, the first one from the first element and the second one for the second element. With the following property is that if we take these pairs and we decode them separately and then add up the decodings of the shares, basically this kind of homomorphic property, if we decode these shares, then this sum of these decodings will be a good estimate of, it can be used as an estimate of X, which typically means that its expectation is equal to X and has low variance. But basically, it can be used to estimate X. And more importantly, the secret sharing property is that each share individually is information theoretically secure. Maybe one way to formulate it, it has 0 differential privacy. Basically, the output distribution on each of those shares individually is fixed and independent of the input. Yes. Right. You could relax these two. So first of all, the question is this the information theoretic security? Yes, it is possible to relax and get better guarantees if you relax, for example, this 0 differential privacy with some kind of computational security. And we have results that do this, but for simplicity, let me start with this definition. And for this particular definition, we show the following result, is that there exists a private frequency estimator, basically a randomizer for private frequency estimation, which communicates this e to the epsilon times log 2q bits, where q is basically it's a kind of it's a security parameter for the aggregation server. We basically will be doing addition modulo q and maybe some potentially additional verification step, making sure that that both servers have obtained the same share. So there is an additional parameter. It's not large. But the point is that the number of bits we'll be sending is domain independent. It scales as e to the epsilon times log q. And for comparison, in the single server setting, we could do with just epsilon bits. I should maybe know that if we are willing to relax the information theoretic security to computational security, cryptographic security, then we can also achieve epsilon times log to q bits, where via a somewhat more involved scheme. Again, I don't have much time to tell you about this algorithm, but basically it's based on a public coin version of this pi rapport algorithm that I've described, pairwise independent rapport. And what we do is we have a public coin part, which we can kind of just send with every message, but there is a secret, not basically the regular message, not the one which uses public coins, will send by secret sharing its indicator vector. That because it has very short length, just epsilon bits, we can secret share an indicator vector. An indicator vector is very easy to secret share. It's just a standard kind of modular secret sharing. And just this algorithm will give us the guarantees that we have promised, and which in practice create huge savings in terms of the communication length over the naive scheme. That's all that I have to say about this result. Let me briefly summarize a bit. So first of all, the main result that I mentioned is local differentially private privacy by itself implies existence of low communication protocols with the same guarantees. It shouldn't be too surprising, but it is still not. It still takes some effort to actually exploit this property in the right way to preserve both privacy and utility, and that's what we show. I've showed that this has a variety of very nice applications for some fundamental problems, such as frequency estimation and mean estimation. There is a large number of open problems, even if some problems are open, even if one wasn't requiring this optimal trade-off between privacy and accuracy, even though we do prefer to get this optimal trade-off. But let me mention just a couple. So one is finding this faster algorithm for mean estimation, which it has this optimal accuracy, and at the same time it has low communication, such as being polynomial in epsilon and log d, low client running time. We want to only pay O of d time on each client, and low server processing. Ideally, we want something that scales as n plus d, not n times d. And there are many more open problems in the secret shared version there, even for frequency estimation. The question of whether one can achieve O of epsilon bits with information theoretic security is open, and for mean estimation, almost everything is open. Certainly at least for optimal accuracy. Suboptimal, you can get it with secret sharing and low communication. That's all that I have to say. Thank you very much. Let me know if you have any questions. No, for some reason the last slide wasn't sure.
Do you have any question? Yeah.
Oh, good question. So so the question is, can we, if I understand correctly, whether we can just use a original local randomizer and secret share its output. So for the high communication randomizer, such as the one in the original rapport, which says this sends this bit vector, that one is easy to secret share. We could just we can secret share, but the problem is that it will have high communication. For the one that I've described and all the ones that I know for low for example, the one we get in the pi rapport, we can no longer, there is the mapping between the message that we send and its decoding is nonlinear. So we cannot directly secret share this description. So we are sending a description of pairwise independent string by having it sort of sending its coordinate in this vector field over vector space over finite field. And that one, yeah, if you like, it doesn't have this homomorphic property. If you just secret share that value, it will not give you anything. What we do is that we show that big part of that message is actually could be sent as public randomness, and only one single field element needs to be sent, is kind of data dependent. And then we secret share an indicator vector for that element. And then we get sort of this homomorphic property that we need for this. But it's a very good question. Yeah, naive. There's a reason we need to do this, and it's because the just directly secret sharing standard randomizers will give you either will give you high communication. Yes. That is a paper at this point, and I don't think I can comment much more beyond that. Yeah, very, very good question. Again, I cannot say how it's justified at Apple, but one natural way is to have a different party, basically a different company like Google providing that service just in the same way as all, like many companies use cloud services of other companies. For example, company A might be relying on another company A or company G to provide its services, and in the same way they can pay for a service which will do this aggregation and in this way ensure non-collusion. But in general, I mean, this is the kind of, yeah, this is a universal problem for secret sharing in general, and then people have ways to deal with it, and maybe I should be asking others here how to best do it. But it is a solvable problem. Thank you. Yeah, so the question is, do we get the central guarantees? Yes, in a way, what we get is one way to call this privacy amplification. But yes, if we can, from the point of view of the server, that only observes the sum or aggregate, we get sort of asymptotically the same guarantees as one would get with central privacy. So basically, yes, aggregation allows us to get to this central DP trade-off between privacy and utility, or at least very close to it. Great question, thank you.
I have a final question to ask you.
Yes.
So you're using the secret sharing approach. If you use the sample model, will you have some better like implications, or can it be applicable instead of using the secret sharing? So
shuffle model would give us strictly weaker guarantees, because naturally the aggregate can always be computed from shuffling. Like so strictly speaking, aggregation always has less information. But for some problems, for example, this frequency estimation, the difference is not that large. Basically, essentially the same things that one would get. Shuffling would already give already pretty much the same guarantees as aggregation. So aggregation is somewhat easier to analyze, especially for some types of noise. For example, Gaussian noise aggregates very nicely into another Gaussian noise. But many of the same things can be already achieved just by shuffling. And also, again, yeah, you also get the same type of guarantee that as long as the shuffler does not collude, or at least one of the shufflers, you can send through many shufflers, at least as long as one of the shufflers does not collude with the server, we'll get the privacy amplification. Thank you. Thank you. Yes, one more question. Very good question. Does the aggregation require kind of users who are non-malicious themselves? That actually depends on the implementation. And there certainly are systems like Prio by Corrigan, Gibbs, and Bonnet that have built-in checks for making sure that we get secret shares and they're all within the right range so that they don't mess up the calculation too much if you send something wrong. So basically, aggregation has to be implemented in a clever way. And again, people here know more about it, I imagine, than I do. But it is possible to build in these checks to make sure that malicious users cannot affect the result too much. Even though naively implementing, just not doing any checks, is obviously very error prone. Like you would otherwise be able to mess up the system quite easily.
Thank you so much.
Thank you. Thank you. Appreciate it.
We're going to be back at 4 p.m.